So hello everyone and welcome to the part 2 of our lecture 6 in which I'm going to cover so-called pigeonhole principle for doing proofs. So this is the last method for doing proofs that we are going to cover in this semester. I also hope that you are all doing well. This has been a challenging week. With the storm and all the power outages. I, for example, still don't have internet at home, so I'm recording these lectures in my office, where the internet is pretty decent. We did our best to accommodate all the exceptions related to quiz 1. So I hope you all did this quiz today on Thursday, if you did not manage to do it on Tuesday and so on. And I hope it all went fine. And we'll start grading it as soon as possible to issue the grades for you. Okay, so let's take a look at what the pigeonhole principle is all about. So pigeonhole principle, or PHP, I'll use this abbreviation a lot, tells us that if m times n plus 1 objects are distributed among n containers, then there must be some container containing at least n plus 1 objects. So if you think about this, it's kind of pretty obvious this is the case, but we can also do a simple proof to actually prove that pigeonhole principle works. And we'll use proof by contradiction to do this. So if you look at the proof, let's try to follow it. So let Kj be the number of objects in container J, and then we have that m times n plus 1 is equal to the sum of the numbers of objects in all of the containers. Now let's assume that we have a counterexample. So this is a proof by contradiction, meaning that all containers have m or fewer objects. So in that case, Kj is less than or equal to m for all j. And then we have that the sum of all this case is less than or equal to this sum m plus m plus m plus m, which is equal to m times n. So we have a contradiction now because the sum has to be actually equal to m times n plus 1, which is greater than m times n. Because we have a contradiction, if you remember our proof by contradiction, we know that there must be at least one container with m plus 1 or more objects. And that finishes our proof of the pigeonhole principle. Okay, let's see now how we can apply the pigeonhole principle to do a couple of proofs. So we'll start with a simple one. So we have the following proposition. If 29 tennis balls are given out to 4 players, then at least one player gets 8 or more balls. So how many containers do we have here? We have 4 containers because there are 4 players. So this is our n. So make sure to practice the pigeonhole principle, and the main, let's say, hardness behind it is to be able to identify how many containers we have, how many items we're distributing, and so on. Once we identify those, it's easy to apply the principle. And whenever you have a proof that has to be solved using pigeonhole principle, you have to write down what the containers and what the objects are and how many of them you have and so on. So that's how you construct the proof. So if you have a problem like this in the quiz, and there will almost certainly be one, make sure to note down in your solution what your containers are, how many you have, what your objects are, how many you have, and how you're distributing them among the containers. Okay, so in this case we have 4 containers. We have 29 objects that we're distributing, so these are the tennis balls. So m times n plus 1, in our case, is 29. And then from that we can compute that m is 7, and so there'll be at least n objects at in one of the containers, and so at least one player we get 8 or more balls, and we prove this proposition. Okay, so that's our first application of the pigeonhole principle. This is a really simple one, so I don't think it was that hard. Like I said, identifying containers and objects and how you distribute them is key to applying the pigeonhole principle, and you always have to write that down in your solution. So, okay, let's look at another one. This one is a little bit more involved. So here's our proposition. Given any 4 integers in Z plus, so any 4 positive integers, some pair of them will have a difference divisible by 3. Okay, so we want to solve this again using the pigeonhole principle. So, we have to again decide how many containers we have and what we're putting in the containers and how. And what are some clues that tell us how many containers we have? Well, the proposition says that we are given 4 integers and some pair of them will have a difference divisible by 3. So the keywords here are 4 integers and pair. So in this case, we have 4 items. And a pair is 2 items. So we want to have a container in which we need to have at least 2 items, and we are distributing 4 items. So from that, it follows that the number of containers should be equal to 3. Okay, so we're going to create these 3 containers, and we're going to label them 0, 1, and 2. And now we have to decide how we are going to distribute 4 positive integers, k1, k2, k3, k4, into these boxes or containers. And we are going to do that based on the remainder that we have after division by 3. In box 0, we are going to put all integers whose remainder when divided by 3 is 0. In box 1, all integers whose remainder when divided by 3 is 1. And in box 2, all integers whose remainder when divided by 3 is 2. And those are the only possibilities, right, for remainders when we are dividing by 3. Okay, so now when we apply our pigeonhole principle of this, we know there has to be at least 1 container. Let's label this container with R that has at least 2 elements, right? Because we're distributing 4 items into 2 containers. And let's call these elements Ki and Kj. So then, because they're in the same container, we know that their remainder when divided by 3 is the same. So we know that Ki is 3 times A plus R, and Kj is 3B plus R for some A, B, and R that are integers. And that follows from the division theorem. So now we want to compute what the difference is, and we want to show it's divisible by 3. So in this case, Ki minus Kj is going to be equal to 3RA plus R minus 3B plus R. If we work on this a little bit, we get that Ki minus Kj is 3 times A minus B. And from that, it follows that Ki minus Kj is equal to some 3p for some integer p. That's closure of subtraction. And from that, we know that ki minus kj is divisible by 3, and hence we proved this original proposition that given any 4 integers, at least 2 will have a difference divisible by 3. Okay, so this concludes our second proof that uses Pigeonhole principle, and make sure to practice these proofs that are of this form. Given some number of integers, prove that their difference is divisible by something, and so on. That's a common usage of the Pigeonhole principle. Okay. Okay. So let's do another one, and this one is even more involved, and it also uses Pigeonhole principle. So here's a proposition: among any 7 positive integers, there are 2 whose sum or difference is divisible by 10. So this proposition has a very similar structure to the previous one. The key difference is that now we are allowing that sum or difference is divisible by 10, not just difference. So let's try to use Pigeonhole principle to prove this. So similar to the previous problem, there has to be a container with at least 2 objects in it, right? Because we're looking at least 2 integers. And so our m plus 1 should be 2, which means that m must be 1. And the number of objects that we have is 7, because we have 7 positive integers. And from that, we can compute that we need 6 boxes or containers. So n must be 6. Okay. So once we figure out that we need 6 containers, the question is now, what is the strategy that we are going to use to place these 7 positive integers in these containers to be able to prove this proposition? And this part requires a little bit of thinking, and even more importantly, it really helps to practice problems to be able to derive this strategy effectively and quickly. Okay, so how would we do it in this case? So we want to do it so that the sum or difference of integers in each of these containers is divisible by 10. So then we'll be able to prove this. And here is the strategy. We want to distribute these integers into 6 containers according to their ones digit. And we'll have a container where this last digit is 0, then a container where the last digit is 1 or 9, 2 or 8, 3 or 7, 4 or 6, and 5. And as an example, let's distribute these 7 integers. So 13 is going to go into the 4th container, 20 into the 1st, and so on. And in the end, we're going to have at least 1 container, this one, where we have 2 numbers, and their sum is obviously divisible by 10. Okay, so this is our strategy. What is the intuition behind it? Well, the intuition is that if 2 numbers that land into a container have the same last digit, then their difference is going to be divisible by 10, while if their digit is not the same, so they fall into one of these 4 containers in the middle, then their sum is going to be divisible by 10, and we can see that based on the remainders. However, we still have to formally show this like we did in the last example. So let's try to do this. Okay. Okay, so let me show these containers here again as a reference. And then we are going to prove that if a pair of numbers lands in the same container, that either their sum or difference is divisible by 10. Okay, so we have two cases here. We have case 1. Same last digit. So in that case, we'll have one number of the form, let's say A is equal to 10 times L plus R, and the other one, let's call it B, is going to be equal to 10 times K plus R. So both of them have the remainder when they're divided by 10 of R, because they have the same last digit. And here L, K, and R are all elements of Z. Okay, so let's abstract A and B is equal to 10 times L plus R minus 10 times K. Sorry, let me erase this. 10 times K plus R. And so this is very similar to the last problem we had. So this is 10 times L minus 10 times K, since R's cancel each other, and that's equal to 10 times L plus K, 10 times L minus K. Times L minus K, and that is equal to 10 times some P because of closure, where P is an element of Z. Okay, and now we proved that their difference is divisible by 10. Okay, so that's the case when they have the same last digit. And this is very similar to the previous problem we proved. Now, case 2 is a little bit different. So that's where they have a different last digit. So this happens when they land in one of these 4 containers in the middle. Now, when we were choosing these last digits, when we were pairing them up like 1 or 9, 2 or 8, 3 or 7, and 4 or 6, this was chosen carefully. They have an interesting property. So if you look at each of these pairs, they add up to 10. And so if a pair lands in one of these 4 containers, then A is going to be equal to 10 times L plus R, while B is going to be equal to 10 times K plus 10 minus R, because the remainders are 1 and 9, or 2 and 8, or 3 and 7, or 4 and 6. Great. And here L, K, and R are elements of Z. So now let's compute the sum. So we have A plus B, and we want to show that the sum is divisible by 10. A plus B is equal to 10 times L plus R plus 10 times K plus 10 minus R. So that's equal to, so R and R cancel again. So we have 10 times L plus 10 times K plus 10. And that is equal to, we can pull the 10 out, 10 times L plus K plus 1. And that is equal to, the same as last time, 10 times P. That's closure. Where P is an element of Z. And there you go. Now we proved that their sum is divisible by 10, and that concludes our proof. So note that in this case, we did use the pigeonhole principle to create the boxes and to prove that we have at least 2 elements in one of these boxes. But then on top of that, we had to do this proof by cases and a direct proof to show that this pair of integers, the sum or the difference is indeed going to be divisible by 10. So it's an example that combines different proof strategies to create a single proof. Okay. Okay. As the last one, I chose a slightly simpler example, I think. So we want to prove using the pigeonhole principle that if we have 26 distinct integers that are chosen at random between 1 and 50, know that 1 and 50 are inclusive, then at least one pair of these numbers is consecutive. In other words, one immediately after the other. Okay. So we have at least one pair. So that means that m plus 1 is equal to 2, which means that m is equal to 1. And then we have 26 items that we are distributing. So m times n plus 1 is equal to 26. And from that, if we plug in m, we can compute that n is equal to 25. Okay, so we need 25 boxes. And we want to show that at least one pair is consecutive. So now we want to define what these boxes should be. Well, it's pretty easy. Let's look at what are the consecutive numbers. So box 1 should be numbers 1 and 2. Box 2 should be numbers 3 and 4, and so on. And then we have box, so this is 1, 2. They'll have 3, 4, so box 5 is going to be 9, 10. And we are going to then keep doing this. We're going to have 41, 42 here, 43, 44, and so on, all the way to 49, 50. So there is 25 such boxes. And so if we pick 26 integers, we place them in these boxes, there's going to be at least one box with 2 integers, which means that at least 2 of these integers are going to be consecutive. And so that concludes this pigeonhole principle proof. So note that, as again, I'm going to stress this out, when you are proving this in your quiz, you have to compute the number of boxes. You have to compute also what your M is. You also have to, draw your boxes and indicate how you are placing your items into the boxes. So you have to indicate the strategy. Otherwise, you don't have a complete proof using the pigeonhole principle. Okay, so that's it. What I had for part 2 of lecture 6. Yeah, it's an interesting way that pigeonhole principle works, and it can be kind of confusing to identify what the items are, how many boxes you need, and so on. So definitely make sure to practice these problems. And if you get stuck, do come to office hours. We have a lot of office hours available, and it's really easy to come to office hours. So please seek help from TAs if you get confused here. Thank you, and stay safe, everyone. And I hope by next week we will all have power and internet back. Bye.